In mathematics, groups and coding theory is a very important topic. So today we start with the some topics from groups and coding theory. Now the first unit is integers. In last video we have seen the basic definitions. Now see what is the definition of prime integer. A prime is a positive integer greater than 1 whose only positive divisors are 1 and itself. So prime integer must be greater than 1 and it has only two types of divisors, 1 and the number itself. For example, 2, 3, 5, 7, these are prime integers. So if you consider 2, then the only positive divisors of 2 are 1 and 2 itself. And 2 is greater than 1, so 2 is a prime integer. Similarly, the only positive divisors of 3 are 1 and 3 itself, so 3 is also a prime integer. But if you consider 1, then by definition 1 is not a prime integer. Now the next definition is when we say that some integer is multiple of another integer. We say an integer s is a multiple of an integer t if there is an integer u such that s equal to t into u. So whenever we can write some integer as some integral multiple of another integer, then we can say that that integer is multiple of another integer. For example, 18 is a multiple of 6 because there is an integer 3 such that 18 is equal to 3 multiplied by 6. Similarly, you can say that 30 is a multiple of 10 because we can write 30 is equal to 10 multiplied by 3. Now, the next important is division algorithm. See what is the statement of division algorithm. Let a and b be two integers with b greater than 0. Then there exist unique integers q and r with the property that a is equal to bq plus r, where 0 less than or equal to r less than b. Now here the integer q in the division algorithm is called as the quotient upon dividing a by b, and the integer r is called as the remainder upon dividing a by b. In school also we study this theorem, but in school that name is not given. So whenever we are given two integers, then we divide the bigger integer by smaller integer, then you get some quotient as well as some remainder, and in that case we write that relation as dividend is equal to divisor into quotient plus remainder. So that is nothing but division algorithm. So whenever there are two integers a and b, a greater than b, then after dividing a by b we get some quotient say q and remainder r. Then we can write a equal to bq plus r, where r is greater than or equal to 0 and less than b. For example, consider a equal to 64 and b equal to 5. Now as 64 is greater than 5, we divide 64 by 5. Then we get 12 as the quotient and 4 as the remainder. So we can write 64 is equal to 5 multiplied by 12 plus 4, where the remainder r is greater than 0 and it is less than b, which is equal to 5. Similarly, consider a equal to 28 and b equal to 7. So if you divide 28 by 7, then we get 4 as the quotient and 0 as the remainder. So we can write 28 is equal to 7 into 4 plus 0. That means we can express a equal to bq plus r, where a is 28, b is 7, q is 4 and r is equal to 0. So this is the division algorithm. Now we see how to find GCD by using division algorithm and how to express it as a linear combination. Now in school we study how to find a GCD of two numbers, but that method is nothing but factorization method. Now here also we find a GCD, but the method we are using is different, that is division algorithm. Now first see what is the definition of greatest common divisor, that is highest common factor of two integers. Now, if a and b are arbitrary integers, then an integer d is said to be a common divisor of a and b if by d divides a and d divides b. Now, as 1 is a divisor of every integer, we can say that 1 is a common divisor of a and b. Similarly, see what are the common divisors of 6 and 8. Now, as 2 divides 6 and 2 divides 8, we can say that 2 is a common divisor of 6 and 8. Similarly, for 20 and 30, 5 divides 20, 5 divides 30. So 5 is a common divisor of 20 and 30. Now not only 5, 10 is also common divisor of 20 and 30 because 10 divides 20 as well as 30. 2 is also common divisor of 20 and 30. It means the common divisor of two integers is not unique, but it should divide both the numbers. Now we can define what is greatest common divisor. Now the greatest common divisor or highest common factor HCF of two non-zero integers a and b is the largest of all common divisors of a and b. Now we denote this GCD of two integers by the symbol GCD in round bracket a comma b. Now what is the alternate definition? An integer d is said to be a greatest common divisor of two non-zero integers a and b if d divides a and d divides b. It means that integer d must be common divisor of a and b. Secondly, if C divides A and C divides B, then C divides D, where C is an integer. What it means? If C is any integer which divides A as well as B, means C is a common divisor of A and B, then every common divisor of A and B must divide D. In this sense, D is nothing but the greatest common divisor of A and B. For example, let us find GCD of 10 and 15. Now first see what are the separate divisors of 10 and 15. Now divisors of 10 are 1, 2, 5 and 10. Similarly, divisors of 15 are 1, 3, 5 and 15. Now what are common divisors? See, 1 is common divisor, 5 is a common divisor. So the common divisors are 1 and 5 only. Now out of these common divisors, 1 divides 5 and 5 divides 5. It means both the common divisors are dividing 5. So what is the GCD of 10 and 15? It is equal to 5. So in this way we can find a GCD of two integers. But this is not actually a method. This is just to understand what is the meaning of the definition. Because if the numbers are very big, then practically it is quite difficult to find divisors of each numbers. We are not using this method. This is just for understanding what is the actual meaning of greatest common divisor. Now see, the next definition is relatively prime or co-prime integers. Two integers a and b are said to be relatively prime or co-prime if GCD of a and b is equal to 1. So if you consider any two integers a and b and their GCD is equal to 1, then we say that they are relatively prime or co-prime integers. For example, the two integers 3 and 7 are co-prime or relatively prime integers because GCD of 3 and 7 is 1. See, if you consider the divisors of 3, then they are 1 and 3. And what are the divisors of 7? 1 and 7. So only common divisor is 1. So GCD of 3 and 7 is 1. It means they are relatively prime or co-prime integers. Now see what is the important thing. If you consider any two consecutive natural numbers, then their GCD is always 1. For example, if I consider 1, 2, 2, 3 or 9, 10, 99, 100. So in this way, for any two consecutive natural numbers, their GCD is always 1. It means any two consecutive natural numbers are relatively prime or co-prime integers. Similarly, GCD of 1920 is 1. So 19 and 20 are relatively prime or co-prime integers. Now, this is one important theorem. For any non-zero integers a and b, there exist integers s and t such that GCD of AB is equal to as plus bt. So whatever is the GCD of given integers a and b, for that GCD we get some integers s and t such that as plus bt. It means we can write the GCD as a linear combination of given integers a and b. Moreover, GCD of AB is the smallest positive integer of the form as plus bt. Now, just now we have seen that the GCD can be expressed as a linear combination of given integers. At that time, we get some integers s and t, but these integers s and t are not unique. Means we may get more than one pair also. See here, now the first linear combination is suppose D is equal to AS plus BT. Then how to find that another combination? For that we can write D equal to AS plus BT plus AB minus AB. So we are adding AB and again we are subtracting AB so that the expression remains equal. Now this is equal to AS plus AB plus BT minus AB. So we are considering AS plus AB in one bracket and remaining two terms in another bracket. Now from first bracket we can take A common and from second we can take B common. So here we have expressed D equal to A into S plus B into T minus A. Initially we have written it as AS plus BT. Now the integers we are getting are different from S and T, which are S plus B and T minus A. So in this way we can find another expression also. Now see the second remark. If A and B are relatively prime, then there exist integers s and t such that s plus bt is 1. So again if they are relatively prime, then their GCD is 1. So 1 is equal to s plus bt. Such integers s and t exist.